Yeah, it's still there.
Okay, no, thank you. Just quickly going back to what I said, electric circuits will take up 18%, 18 marks out of the 150, which is roughly 10% of the paper will go to, or yes, will go to electric circuits. So the formulas that we have, or symbols that we need to keep in mind will be the ones that I've highlighted already. I have E for EMF, small letter R for internal resistance of the battery. We have capital letter R for internal for resistance of the external circuit. We also have now I can't do much here. I wanna write my pen has disappeared. I think it's back. Okay. And then we have capital letter R, that capital letter I rather, that will indicate current. We have capital letter Q or small letter q, mainly it will be a small letter q for charge. And then we have delta T for time, V for potential difference, and then the capital letter W for work done. And lastly, we'll also be looking at the symbol of capital letter P that will represent power. So those are the symbols that we will be focusing on. We're gonna see them a lot in the equations that we're going to be using today. Without wasting time, let me move on to the next slide. Okay, go back. Let me just quickly check. Yeah, go back. Okay. Yeah, no. Okay. From the grade 10 syllabus, this is what we need to know. I'm going to try and explain as much as I can here on this slide with terms of grade 10 because I'm not going to have enough opportunity to actually go back to the content in detail of grade 10. So it says we need to be able to identify EMF, differentiate between EMF and potential difference. We need to be able to define current. We also need to know how to, what are used, what are the apparatus that we use to measure potential difference and current. Now, typically when we look at a circuit, we have symbols that we use in a circuit. And those are important symbols for us to remember. We have a symbol in the circuit drawing. We have some of the following symbols. If we want to represent a bulb, if we want to represent a bulb or a resistor, we would use a symbol like that. That is a symbol that we can use to represent a bulb. That's a type of resistor. And then we also would find something like that. That would be also a symbol that we use to represent a resistor. So if we want to talk about a typical resistor, meaning at home, when you're looking at the appliances at home, your TV, your kettle, your stove, all of those resistors, everything that consumes electricity, we would use this symbol here. But if we want to be specific to talk about a specific type of resistor, then we'll use a symbol or a bulb that will tell you that we are talking to a specific resistor, something that consumes electricity. And then you would find symbols like these. That would be a symbol that represents an ammeter. An ammeter is a device that we use to measure current, the flow of charge in a circuit. And always remember that ammeter is connected in series. That means current flows through your ammeter, and it does not have potential difference that we normally measure. And then we have a symbol like that one that is for voltmeter. This is connected across 2 points. That voltmeter, we use it to measure the potential difference between 2 points. So we'll look at an amount of them, but typically this is what we normally would find in our circuit. And then the next symbol that you would find there is a battery. A battery, obviously, is the source of potential difference, is the power source. That's where everything begins. So we are going to be looking at those symbols. Here we need to understand, in grade 10, we talk about EMF. When we talk about EMF is defined as the maximum energy provided per unit coulomb of charge. And I want you to remember those words. It's the maximum. It's the maximum. So that means if you are holding a cell or a battery in our common language, if you are holding a cell and you look at the outside of the cell, what's written outside, they will say that the cell has 1,5 volts. The reading that you are seeing there on a brand new cell, that reading is what we call EMF. That's the maximum energy provided by the battery per unit coulomb of charge. And as soon as the battery starts to be in use, as soon as we use the battery, the battery will provide obviously EMF once. As soon as energy starts to flow or charges start to flow inside the circuit, we now move from EMF and we are getting into what we call terminal potential difference. That means the reading that we'll start to observe, that reading will now be called terminal potential difference. It's no longer EMF, because as we use the battery, it starts to lose energy as well. So the moment it's no longer providing the maximum, it's no longer called EMF, it is called potential difference. So potential difference will be represented by the symbol V. Potential difference represented by the symbol V is measured in what we call volts. So a good example of potential difference in grade 10, we spoke about potential difference. We said that V, because it's the work done per unit coulomb of charge, will be equal to W over Q. Now, it's the work done per unit coulomb of charge. So that's the work done over per charge, the energy needed to move a certain amount of charges. That's potential difference. So it is imperative that we understand the difference between EMF and terminal potential difference. Terminal comes after EMF, but EMF is the maximum, and the terminal potential difference is just defined as energy provided per unit coulomb of charge. It's just defined as energy provided, but EMF is defined as the maximum energy provided per unit coulomb of charge. And both of them, they have the same unit of measure, which you know as volts. They have the same unit of measure. Then the second thing that we also need to highlight in grade 10, or from grade 10 as well, is current, the flow of charge, I. Current is defined as the flow of charge. This is the one bullet in electric circuits that I personally feel that is the most important, because it is through current that we are able to connect the entire circuit. It is through current that we are able to find other parts of the circuit. So for me, I would say, if you were to ask me what would be the one important thing in your circuit, I would tell you that for me, it is current. Current is the one component in all of these components that we find in the circuit that can travel throughout the entire circuit. So that means if we have current for the circuit, half of the battle is won. So current is defined by, we use the symbol capital letter I, and from grade 10, we are saying it's called the rate flow of charge. Remember the definitions is the rate flow of charge. So that means it's charge, Q divided by delta T. And it's measured in what we know as amperes, named after Sir Ampere. So that's the unit measure of current. We use what we call conventional current. Conventional current is the flow of positive charges. That's the current that we are using in electrical circuits. We use what we call conventional current. This is the flow of positive. That's the flow of positive charges. So the flow of positive charges, which says to I, or says to you and I, that the charges that when we connect the battery, the flow of charge will come from the positive terminal of the battery to the negative terminal. So we are moving from the positive terminal to the negative terminal of the battery, which is why we say we are using conventional current. This is the agreed upon current. This is the current that it was agreed that this is the current that we're going to indicate when we are dealing with electric circuits. From there, it says in grade 10 that you are expected to know how to draw a circuit diagram correctly indicating how ammeter must be connected. Now, the ammeter, like I said earlier, must be connected in series. We'll also touch on the two types of connections. It must be connected in series, and voltmeter must be connected across. Now, so we will see. We will just touch a little bit on that so that we have enough background when it comes to that. The next bullet that we also need to look at is resistance. Resistance refers to the opposition of the electric current. Now, the devices that we use at home, they have what they do. Let's take a bulb, for example. Current flows through the bulb via wires. And then when you switch on the switch, you press the switch and you switch it on. The bulb, what it does is to consume the energy that the current is coming with. So it takes the energy that current is carrying and converts that energy from electrical to light. Your kettle or your stove will convert that energy from electrical to heat, for example, or your heater, your TV, and every appliance at home. So the measure of that usage, we call it resistance. Now, that measure is called resistance. So resistance is the opposition to the flow of current. Opposition to the flow of current is denoted with a capital letter R. It's denoted with a capital letter R, and it's measured in what we call ohms. And we calculate it because it's the opposition to the rate flow of charge. It's V over I. If we were to calculate resistance, we would use that. So that says it's 1 volt per ampere. Now, the unit measure of resistance, which is 1 ohm, is 1 volt per ampere, which this will be the typical formula we use to calculate resistance. However, the symbol or SI unit for resistance is ohms. The SI unit for resistance we know is ohms. So we also needed to know resistors that are connected in series. How do we calculate resistors that are connected in series? We also need to know how to calculate the resistance of resistors that are connected in parallel. So we are going to roughly go through such because it is very, very important for you to know how to calculate the resistance of resistors connected in series, the resistance of resistors connected in parallel. So we are going to summarize that quickly. We're just going to do that very quickly as well, just so that we have sufficient background on what we are going to be looking at. In terms of grade 12, there isn't much. We are just adding internal resistance. Most of us already were exposed to it in grade 11. So we just need to get the background out of the way. So that was the syllabus in grade 10. Now, on this circuit, I want to highlight those things that I was talking about. When we have two types of connections. We have what we call a series connection, and then we have what we call a parallel connection. We need to know what happens to current when we have a series connection. We need to know what happens to current when we have a parallel connection. So we are focusing on the three. We need to know what happens to potential difference. We need to know what happens to current. And we also need to know what happens to resistance when we have the two types of connection. Now, what is a series connection? A series connection is a connection where current flows in one pathway. Current flows in one pathway. That means that we do not have multiple multiple channels where current can flow. Remember, we said current is the flow of charge, just like a river or a flow of water. So current flows from the battery, and the type of current that we have moving from the battery is what we call total current. So you need to have those subscripts be underneath so that you can indicate so that you can also see the type of current that's flowing. So current flows from the positive terminal of the battery. It goes down, passes A1, gets to R1, gets to A2, R2, and then A3, and then comes back to the battery. The current that flows out of the battery, that current, we call it I total. So the moment we are drawing the flow of current, it is important for you to remember the one that comes out of the battery, we call it I total. And as you can see with that, the flow that I've indicated there, the current that's coming out of the battery is the same current that's passing in A1. It's the same current that is passing in resistor 1 as well. Ammeter 2 is the same current, resistor 2 is the same current, ammeter 3 is also the same current. Remember, current will not flow. It does not flow on voltmeters. We will not have current flowing in voltmeter, which is why the same. If we have a series connection, current will be equal throughout the 3 resistors, or it will be the same throughout all your ammeters, because current that's flowing is the same one. We are not changing it. Are we together? I hope we are still together there. We have the same current flowing, and then potential difference. Potential difference, however, will be in a series connection, potential difference is divided. So series connections are known as potential difference dividers. Now, that means the EMF from the battery is the total potential difference of the circuit. The moment current flows, this resistor here is going to use up energy, and that resistor there is going to use up its own energy as well. So that means the current of the potential difference of the circuit, the potential difference in V1, depending on the type of resistors that we have in there connected. The potential difference in V1 might not necessarily be the same as potential difference in V2. However, the sum of the two, the sum of the potential difference in voltmeter 1 and potential difference in voltmeter 2, their sum will equal to the potential difference in V3. This is supposed to be V3 there. Now, so, or that one as well. So they will be equal. Their potential difference is the sum. So it's divided. Potential difference is divided on a series connection, but current remains the same. When we come to a parallel connection, the same thing that we did on the other side. Look at the current flow, and you can see the current exiting from the battery. It's going to pass A1. When it reaches this point, now current finds itself in a position where it has to be divided. So when we want to divide current, then we'll have current flowing in that direction. And then we'll have current flowing in this direction as well, which is why they say parallel connections is where current travels in multiple pathways. It is important that the current that is flowing out here, we call it I total. But when the I total reaches this point, it's now going to be divided. It splits into 2. Some of it will be coming this way, which we'll call it I1. I1 because it's the current flowing in resistor 1. And then the current flowing here, we call it I2. That is the current flowing in resistor 2. I hope that is clear. And then the current in resistor 2 and resistor 1, they are going to meet at that point as well, returning back to what we know as total current. And then it will return out as total current there. What is important to note when it comes to when it comes to when it comes to current here. What is important to note is that current here, since we are saying current is divided, that means current in a parallel connection, I total will be the sum of the individual currents flowing in all those resistors. It is the sum. In our case here, we have current flowing in resistor 1 and current flowing in resistor 2. So those currents, the sum of the two currents will give us the total current flow of the circuit. And then potential difference in a parallel connection. I want you to also remember, parallel connection here refers to these guys only. Current that is divided refers to those resistors only. Now, potential difference across parallel connection, potential difference across parallel connection remains the same. It remains the same. That means resistor 1 will observe the same potential difference flowing in resistor 1 and the same potential difference in resistor 2. However, it does not matter if the resistors are the same or not. No, it does not matter if resistors are the same or not. As long as the resistors are connected in parallel, they will have the same potential difference, which means the potential difference that we're going to observe here will be equal to the potential difference observed there and the potential difference observed at V3. Now, and as well, because we don't have any other resistance outside of the circuit, the potential difference that will be observed at EMF there will also be the same as the one that we see here, there, and there. Now, okay, I hope I've tried to cover as much as we can. So we need to now talk about resistance. If we talk about resistance, how do we calculate resistance in a series connection? That would be the effective resistance of the circuit. Effective resistance refers to total resistance of the circuit, external circuit. The total resistance of the circuit will be R1 plus R2 and so on. Depending on the number of resistors that we have in series, that is the effective resistance, or R total. Total resistance of the external circuit will be R1 plus R2 in a series connection. When we come to a parallel connection, the effective resistance of the circuit, or R total, will be equal to 1 over R1 plus 1 over R2, and so on. Now, so that's how we calculate resistance in parallel, and that's how we calculate resistance in series. Okay, I think we are still together so far. Moving on. Just quickly, I have already highlighted to this that effective resistance of a series connection, that's the formula we use to calculate it, and the effective resistance of a parallel connection, that's the formula that we use to calculate it. Now, so it is important. Unfortunately, I will not have sufficient time for us to go through it, but your teachers will get the presentation. There are some of activities where you need to practice a lot in order for you to understand what we are talking about here. Okay, and then moving forward, almost everything here are those that we have covered now. This is grade 11. In addition to what we talked about in grade 10. In grade 11, this is where we introduce what we call Ohm's law. Now, Ohm's law explains the relationship between the three, which is current, potential difference, and resistance, provided that the circuit is operating at constant temperature. Now, so we need to know how to define. This is another definition, a term that you must know. We need to know how to define Ohm's law. Is the potential difference across terminal ends of a conductor is equal to, is the potential difference across the terminal ends of a conductor is directly proportional to the current flowing through the conductor and at constant temperature. It's another term that we must know. And then we should also know the difference between an ohmic and a non-ohmic conductor. Because Ohm's law says that current is directly proportional to potential difference. And it also says that resistance is directly proportional to potential difference. However, he also said current and resistance are inversely proportional. That means if we increase current, we will increase potential difference, provided resistance remains constant. If we increase resistance, we will also increase potential difference, provided that current remains constant. But if we were to increase current, then we will have to decrease resistance, provided that potential difference remains constant. If you recall from what we just spoke about, we just said that resistance in parallel, resistance in parallel, or potential difference on a parallel connection, potential difference remains the same. So that relationship, you can also see it there. Okay. And then from there, we need to know how to solve circuits using Ohm's law. So let us quickly just go through for grade 12, this will touch a lot on it later, but in grade 12, we are going to include now what we call internal resistance. We'll talk about it more. So let us just briefly, for 5 minutes, I'm just interested in the following questions, just for 5 minutes. Try and answer question 2 and question 4. Just quickly answer those 2 questions, question 2 and question 4. There is something that I need to highlight there for you. Please answer those. I don't know if I'm able to view a timer here, but the time now is 8:32. So we will come back at 8:37. At 8:37, I'll be coming back to hear from you what your responses were. Quickly try those 2 questions, question 2 and question 4. Okay, we are back. Let me just quickly check if we were able to answer this question. Question 2, what it says was the potential what is the potential difference? The highlight. It says we need to know what is the potential difference between 2 points in a circuit when a 60 coulomb of charge transfers 4,000 joules of energy as it moves between 2 points. So to answer that question, it's asking us to calculate V in terms of work done over charge. And the work done over charge, we have work done of 4,000 divided by charge, which is 80. Now, and you will get your answer there as you press your calculator. It will give you your answer there. And then for question 4, it says the potential difference across a bulb in an electric circuit is 15 volts. The potential difference is 15 volts. Fine. How many joules of electrical energy, we are looking now for energy, are changed into light and heat energy when there is a current, when we have a current of 2 amperes in the light flowing for 10 seconds. Now, what we are given here is that we have V, which is the potential difference across the bulb. We are looking for capital letter W, which is the work done. And then we are also given current, which is I. Now, we're also given current flowing there in the circuit. If you go to your data sheets, the formula that we are looking for here is on energy. And the formula says we have capital letter W, we are looking for work done. And if I have work done, if I have potential difference, like I have potential difference there, I have current, I, and I also have time, delta T. You will find the formula there. That's the formula we use to calculate electrical energy or work done. And that will be 15 times 2 times 10. No, it will be 15 times 2 times 10. Then it will give you 300 joules. If I'm not mistaken, it should be 300 joules of energy. I just wanted to highlight that for you as well. I wanted to highlight this particularly because we are going to talk about this when we get to power. Hope we were clear. These are the questions that we use. So when we calculate total resistance or effective resistance in a series connection, this is a series connection because you can see that current is flowing in one pathway. So that would be 2 ohms plus 3 ohms plus 5 ohms, and that will give us 10 ohms. It's a series connection. Now, current is flowing in one pathway. But if you look at that question, current comes in there and then it's divided into 3. We can see that current here is divided into 3. So that means we have current for the 2 ohm resistor, current for the 3 ohm resistor, and current for the 5 ohm resistor. Now, if we were to calculate the effective resistance of this parallel connection, then that would mean I have effective resistance or R parallel will be equal to 1 out of 1 over the resistance. The first one is 2 plus the resistance, second one is 3 ohms plus that one will also be 5 ohms. And then you are able to get your effective resistance for that parallel connection. Now, if you look at question C here, we have current coming in, passing through the 2 ohm resistor, but as it reaches this point, current now is split. And when we split it, we can see that current, some of it goes that direction and some of it goes in that direction, which says we have current in the 3 ohm resistor and we have current in the 5 ohm resistor. That the two currents will meet now at point B. Now, so that this says to you and I, we have a series 2 ohm resistor now is connected in series, and 3, 2, and 5 ohms are connected in parallel. So the question says the 3 and 5 ohm resistors are connected in series, and their effective resistance is they're connected in parallel, and their effective resistance is connected in series to the 2 ohm resistor. Now, so the effective resistance of this connection, this is a dual connection where we have parallel and series in one circuit. The effective resistance of this connection will be the resistance in series plus the resistance in parallel. The sum of the resistance in series, what we can see is that it's 2 ohms. And what is the resistance in parallel? The resistance in parallel is 1 out of 1 over 3 plus 1 over 5. So that would be the sum, the effective resistance of a connection like this one. Now, where we have parallel connected to a series connection. So the effective resistance in this connection will be total. The total resistance will be the resistance in series, total resistance in series, plus the total resistance in parallel. I hope you have noted that. I just want to rush through now. We are running out of time. Yes, this is what we have been explaining to all on. This is just a summary of what we have highlighted, that the total resistance in series is the sum of the individual resistors, and their potential difference will also be the sum of those resistors. Now, so to sum up what we have just said, we said resistors in series, the total resistance increases as more resistors are added. Remember that this is for the word questions, those questions where you have to explain. So remember that the total resistance of a series connection will increase as we increase the number of resistors, which therefore means the opposite is true for it as well, that if we decrease the number of resistors, the total resistance for a series connection will also decrease. Now, in a series connection as well, if one resistor is not working, all the circuit is also broken down. Now, if a resistor bends out, if one resistor bends out, it cuts off the current flow for the entire circuit. So that means the circuit will not function if one resistor bends out. Okay, and also important to remember that the total resistance of the series connection will always be greater than one of the highest resistors or resistance in that circuit, meaning the total resistance of the circuit will always be greater than the biggest resistor in the circuit there. Okay. And also important for us to note is that in a series connection, power will be the greatest with resistor with the greatest resistance. In a series connection, the greatest power belongs to a resistor that has the highest resistance, according to that formula there. It will have the highest. And if we have to look at another formula, it says that resistor with the greatest resistance will also have the greatest voltmeter reading. Now, the resistor with the greatest resistance will also have the highest voltmeter reading. It will have the highest potential difference, according to Ohm's law. And because of that, it will also have the biggest power. It will have the highest power of the circuit. That is for series connections. In parallel connections, there we can note the following: the equivalence resistance or effective resistance is always less than the resistance in the circuit, the biggest resistor or the smallest resistor in the circuit. It will always be less. So that means with parallel connection, we are reducing the resistance of resistors. The equivalence, the total resistance of the parallel connection will be smaller than the smallest resistor in that group. And the parallel connection as well, each device operates independently. Unlike in series, we said that in series, if one of them breaks down, the whole circuit will not function. But in parallel, if one of the devices breaks down, the circuit will still function, which is why it says each device is operating there independently. Now, And all of them, like we have already highlighted, will have the same potential difference and current will flow in different paths. Now, one thing to remember, the resistor with the lowest resistance will have the highest current. The resistor in a parallel connection with the lowest resistance will have the highest current. Remember, we said current is inversely proportional to resistance. So that means if resistance is low, current will be high. And if resistance is high, then current will be low. And that's the one thing you need to also take note. The current of the resistor with the lowest resistance will be the highest there. Okay, I just want to move now. These are just formulas that you can read through with your teacher as well. For now, I just want to show you this activity quickly. And this is where everything begins. If you are able to fill the whole table here, if you're able to answer each and every question that you find in these slides, there is no question on electric circuits that will puzzle you. All you have to do is to fill the table here and you will have your answer. Okay, let's just quickly look at this question. This question says here that we have a circuit connection like that, and we are only going to attempt one in each of the questions. Current is flowing out from the positive terminal and it passes the ammeter there and then reaches this point. What type of current flows out here? The type of current that's flowing out of the battery, we know it as total current. And this current passes and reaches a connection. When it reaches this connection, some of the current goes up, current is now divided, and some of the current goes down. Current is also divided. So we now need to highlight that this current that we are going to see here, this is what we call current 1, and that is what we call current 2. Current 1 is the current that's flowing in the R1 resistor, and current 2 is the current that is flowing in the R2 resistor. And then from there, current merges and goes out, and we can see what we want to see there. We are going to say that the battery has neglectable internal resistance. That means we are ignoring the internal resistance of the battery for now. For the purpose of this activity, this is to ensure and expose you to multiple ways in which the questions can be asked. So if we look at question A there, what we are given is the effective resistance in parallel. They say the effective resistance in parallel is 6 ohm. The resistance of resistor 1 is 12. So we have 12 ohms for resistor 1. And then they say the potential difference in V2. Where is V2? Here is V2. Potential difference in V2 is 6 volts. That's all. So we know the total resistance of the parallel connection. We know the resistance of resistor 1. We know potential difference in V2. We don't know the reading in ammeter 1, ammeter 2, and that ammeter there. All the potential difference are caused there and the potential difference in V1. Now, however, we can start with the basics that we have already highlighted. What we know is that in a parallel connection, potential difference remains the same. So that means the potential difference in V2 will be equal to the potential difference in V1. So that means, therefore, V1 will be equal to 6 volts because V2 and V1 are connected in parallel. We fine? Okay. And then from there, because I now know the resistance in resistor 1, and I also have the potential difference in V1, then I can calculate the current flowing in V1 as well. To say that, well, I1 will be equal to V1 divided by R1. That is current for resistor 1 is equal to potential difference in resistor 1, and that would be potential difference there is 6, and the current resistance there is 12. So that would be 0.5 amperes. You are already able to now answer one of them. That is the current that is flowing in A1. The current that is flowing in A1 is 0.5 amperes. We good? Okay. And then the question would be, what else can I answer without doing a lot of calculations? Well, we can also get the potential difference, EMF of the circuit. The EMF of the circuit, because we don't have any other resistance outside. We only have one resistance that is in parallel. Then the EMF will be equal to the potential difference of the parallel connection. So that means the reading in V there will also be 6 volts. Then, okay, and then from there we are now able to calculate everything else that we need. Let's move to calculating the resistance of resistor 2. The resistance of resistor 2 will be, because it's a parallel connection, 1 over R total is equal to 1 over R1 plus 1 out of R2. 1 out of R1, R1 is equal to R1 is equal to let me just erase quickly. R1 will be equal to, so R total will be equal to, we have already given R total, which is 6 ohms, and 1 out of R1 we were given as 12, plus 1 over R2 is what we do not have. However, we can now get R1 to say, well, R2 will be equal to 1 out of 1 over 6 minus 1 over 12. And if we press our calculators there, we'll get
okay.
Are you talking to me or you just unmuted your mic?
I'm wanting and say, yeah. Yeah, boo. I'm wanting you to. We're opening the process.
Asa, can you please mute yourself? Thank you. As we were. So once you get the answer here, you have already calculated the resistance of resistor 2. And once you have the resistance of resistor 2, then you can calculate the current flowing in resistor 2. And lastly, you just add the two currents and you get the total current of the circuit. Then you get the total current of the circuit. For those of us who are not confident enough with electric circuits, this activity and the next one are the ones that I would suggest that you start with. Before you can even worry about internal resistance and everything else, start here. This is where you must begin. If you are able to grasp here, because a lot of marks are actually here. Your question papers that we're going to look at as well, you will see, they all want us to be able to do this first. So this is the base of everything. If we know this basic, then there is no question. There is no question that you're going to come across which will be difficult for you to answer. Let's take another example quickly. Unfortunately, I don't have a calculator with me, but if you have the answers to all these questions that I'm asking, or that we need to calculate, just indicate to me, talk to me. I'm here also. So this is the current flow. I hope you've been paying attention to what I do. Every time I look at a circuit, I indicate the type of current, the flow of current. Even yourself, when you are writing your examination, do the same. When you're writing your test as well, do the same. Start with, even before you read the questions and everything, look at the circuit diagram, draw the flow of charge. That will tell you what is in series, what is in parallel. Now, the current that's flowing out of the battery always, the current flowing out of the battery is the total current. So that means the current that's passing in A1 is the total current of the circuit. The current that is passing in at R1 there is also the total current of the circuit. So that means we are looking for I total there. However, this I total, when it reaches this point, it's divided into two. That means there is I in resistor 2 and I in resistor 3. So that's I2 and I3. That says resistor 2 and resistor 3 are connected in parallel, and their effective resistance is connected in series with resistor 1. So this is a dual connection. This is also a good example of what the examiners use. Examiners prefer they are limited to asking you about 4 resistors. So they will either go this route or they will go that route. They are limited to 4 resistors in a circuit. So if you look at that, we know this is a parallel connection. That means R2 and R3 are connected in parallel. Because they are in parallel, the potential difference in V2 and the potential difference in V3 and the potential difference in V4 are the same. Then, potential difference in V2, V3, V4 will be the same. This is a parallel connection. When you get to R1 there, the total V, this V, EMF of the circuit, V will be equal to the potential difference in V1 plus the potential difference in V4 plus the potential difference in V4. Now, why? Because V1, R1, and the parallel connection are connected in series. They are connected in series. So the effective resistance of the parallel connection is connected in series to R1, which is why the EMF of the circuit, V, will be equal to the sum of the potential difference in V1 and the potential difference in V4. So the moment we see that, already we can highlight, or we can see that, well, all of the questions are answered for us. Because if I know the reading in R1, the reading in R2, and the reading in R3, I can calculate the effective resistance of the whole circuit. The effective resistance of the whole circuit, R total for the whole circuit, will be the resistance in series plus the resistance in parallel. Effective resistance in series plus the effective resistance in parallel, which is, what is the resistance in series? My resistance in series is just at R1, that is 3. Added to, what is my resistance in parallel? My resistance in parallel, I have 1 over 2 plus 1 over 1. Now, and that will give me the total resistance of the circuit. That gives me the total resistance of the circuit. And I think that would be 5, if I'm not mistaken. Yeah, it will be 5 ohms, if I'm not mistaken. And then from there, once I have that, I have R total, I have V, here is V, that V. And what is that? That is the EMF of the circuit. I have V total. So I have I total, I have R total, I have V total. Then I can calculate I total. So I total times R total according to Ohm's law. V total is equal to I total times R total according to Ohm's law. V is equal to IR. Then I can calculate I, and I total, which is the current that is flowing out of the battery, will be equal to V, which is 1,5, divided by 5. And I think it will be 0,3, if I'm not mistaken, amperes. If I'm not mistaken, it will be 0,3. Already we have mastered the art. So we have I total. If we know I total here, there, we have I total. We have the resistance of R1. We can now find V1. You see, that's how easy it is. if I know I total there, then I can see the resistance of R1 is 3. There it is. Then I can find V1, the reading on V1. We use the same formula. We say, well, V1 will be equal to, what do I see? I see I total passing on R1 times resistance of resistor 1. And what would be my answer? That's 0.3 multiplied by the resistance of resistor 1 is 3. And I think that will be 0.9 if I'm not mistaken. 0.9 volts. If I now know that this is 0.9 volts. This is 0.9 volts. And from there, we have already highlighted there that the total potential difference, EMF, is equal to V1 plus V4. So we can get the reading on V4 because we have V1, that is 1.5 equal to, V total is 1.5, it was given to us here. We saw it there. And then V1, we have calculated it, is 0.9 plus V4. Then we can get our answer and we see that V4 will be equal to, the reading on V4 will be 1.5 minus 0.9. And 1.5 minus 0.9 will be, if I'm not wrong, I think 0.6. Stand to be corrected. Okay, and in that instance, we have already answered most, because if I know that V4 is 0.6, that will be 0.6, then V3 is connected in parallel, that will also be 0.6. V2 is connected in parallel, that will also be 0.6. And half of the job is done. Because if I have half of the job done already, I know the current flowing here, we said is 0.3. Now, we calculated it there already. So current in A2 and A1, we can calculate. That will be I2 is equal to V over R. The reading on V2, we said, is 0.6 divided by the resistance of 2. There it is. And the reading on I3 will also be V over R, and that would mean I have 0.6 divided by, which is our potential difference, divided by R, which is the resistance there. The resistance is 2. So you can get your answer there. Then that would have answered most of your questions there. So please, if you are not comfortable, if you are not yet there with circuits, this is where I would suggest you go. Start with this table. Start with these 2 slides. These are the 2 slides that I always encourage learners to do. We start here. We answer this table. Make sure that we are able to master this table. And once we're able to master this, then you are fine. You will be fine. I hope there are no questions. Are there questions? If you have a question, you can raise your hand or unmute yourself. So that we move on now to grade 12 circuits. This is just grade 10, typical questions that you did in grade 10. But pay attention to what I was highlighting here. What I was highlighting is that once you know the type of connection you have, you are sorted. So that means all these 3 resistors are connected in series. If you go here, you can see the type of connection is that the 2 ohm is in series, but the 24 and 8 ohm are connected in parallel. So the effective resistance is in series to the 2 ohm resistor. We're good? Hope we are good. And then this is the relationship, Ohm's law relationship. Now, here they want you to look at the relationship is between current and potential difference. Current is on your Y, potential difference is on your X-axis. One of the conductors, X, has a straight line, the other one is bending, which is Y. So this will be known as an ohmic conductor, and that will be a non-ohmic conductor. Why? Because it does not obey Ohm's law. Ohm's law says current is directly proportional to potential difference. So that would be the questions that they asked there. And it was also interesting that they put in power there, the question of amount of energy, and that would be power. They gave you power and potential difference. It was also an interesting question you did in grade 10, in grade 11 rather. Okay, and then from there they wanted you to cost it. We'll look at those when we finish grade 12. So in grade 12, which is today now, these are the components, the formulas that we have already discussed on that side. We have looked at this formula in the data sheet. We have highlighted most of the symbols, actually all of the symbols that we find here. We have already highlighted and named them. What we only need to do now is to move on to internal resistance. So what is internal resistance? When you are working with your cell phone, when you are busy with your cell phone, playing with your cell phone, at some point, when you hold your cell phone in your hand starts to feel warm. It gets hot, and then some of us will put it in the freezer to drop the temperature because you want to work with it very fast. Or some of us will just let it go, or we leave it alone for some time so that it does not burn out. That heat that you feel at the back of your cell phone, that heat is due to what we call internal resistance. Now, what is happening inside the battery? Remember, the battery provides energy to charges. So imagine, take this picture. Imagine you have 1,000 people. You have 1,000 people collecting water. There is fire somewhere, and people are coming to collect water from the reservoir. This will be water in the reservoir, and people are coming with buckets to collect water to go and put out the fire. Now, when people rush, if 1,000 people rush to the same place to go and collect water, obviously some are going to bump on one another. We are going to bump on each other, and as we bump on each other, some of the water that we are collecting is going to fall down. Some of the water, as you are running towards the fire there, some of that water will also get lost in the way. That's why when you read the question, they always say the wires have neglectable internal resistance, or the resistance of the wires is neglectable. That's because as the charges get inside the battery here, as charges are flown out of the battery, they gain energy. They are holding buckets of energy, and they are running with those buckets of energy throughout the entire circuit. But as they reach the inside of the battery, these charges are bumping on each other. And as things bump on one another, friction, they will cause friction. And that friction generates energy, it uses energy. So, and it converts energy into heat. So energy is lost in a battery, in the inside of the battery. Energy is lost, and that energy is lost due to friction because charges are colliding with each other as they are moving through the battery. And because of that loss of energy, and I want you to remember it's loss. This is the lost energy. Because of that lost energy, we call it potential difference. Remember, we said potential difference is the energy provided per unit coulomb of charge. So energy is lost, and some of the energy goes out. But the battery provides 1,5. The battery does not compensate for the lost energy. The battery just provides 1,5. It does not say, it does not have additional. So it says, I have 1,5 volts. If some of it is lost because you guys cannot work together, there's nothing I can do. I can only give you 1,5. So we need to take into account the amount that is lost and the amount that goes to put out the fire. Now, the amount of water that is lost due to us not being able to work together, and the amount of water that goes out. We need to observe that. That's why we study internal resistance. We study internal resistance so that we know how effective will a battery be in a connection. If we know the internal resistance of the battery, then we are able to calculate how much of that energy that is required to light everything else will we need. And we also need to look out of how is it that we can try and minimize the amount of energy that we lost. So the EMF, as you see it here, EMF is potential difference. That's the maximum. So that's the maximum potential difference. That is potential difference that is lost due to internal resistance. And the potential difference that is out, which we call the terminal potential difference. So we have EMF equal to potential difference lost plus terminal potential difference. Okay, so what is terminal potential difference? This is terminal potential difference. That is the energy provided to the external circuit. So meaning in a circuit, we have two types of circuits. We have what we call the internal circuit, and we have what we call the external circuit. External circuit is the circuit where we see all your resistors and your bulbs and everything else. Those are the ones that go out. And these ones, they use what we call terminal potential difference, V terminal. They use terminal potential difference. Whereas the second circuit that we have is the internal circuit, which we note by the symbol small letter R. That is internal resistance. This is external resistance. This is the resistance that you and I have been calculating for the past hour. This one is the one that we're introducing now. But how do we calculate potential difference? We calculate potential difference using Ohm's law by saying current times resistance. And current times resistance, if this is for the external circuit and that is for the internal circuit, then we can see that the current that is flowing out of the battery is the same current that's going back into the battery. So that's why this current is the same as that current, is the total current, is the main current of the circuit. And if you factorize that, when we factor it, we can see that total current is a common factor. So that gives us our equation that we use to calculate EMF, that E is equal to total current. This is the main current. Yeah. Total current bracket total or effective resistance of the external circuit, that parallel and series connection that we're talking about, their total here, plus the resistance of the internal resistance of the battery. Yeah. So this is the formula that we use to calculate the EMF, the EMF of the circuit. So here now brings the question of, when do I see, Mr. Mutamai, when do I see that right now I'm dealing with EMF, and when do I see that right now I'm dealing with potential difference? Well, let's try and correct that. I'm going to draw for you here 2 circuits. In one circuit, the switch is open, and in the other circuit, the switch will be closed. Now, it's the same thing. Everything is the same. The only difference is these things, the switches. One has an open switch, the other one has a closed switch. If the main switch at your home, the box, electricity box, if the main switch on the electricity box is cut off, if we close it, nothing in the house works. We all know that. So meaning the current the current that's passing through a switch, the main current, if it passes through a switch and the switch is open, the external circuit is not operational. Now, the current that's flowing out is passing through this, and this becomes our main switch. So that means the external circuit is not operating. Everything outside of this circuit will not operate. So meaning the potential difference outside is 0 because the main switch is open. If the main switch is open, external circuit does not operate. So the examiner will ask you, what will be the reading on that voltmeter there? And when he asks you what's the reading on that voltmeter, you must be able to tell him that there is no potential difference there because the main switch is open. Nothing operates in the house if we turn the main switch on. But something else, that does not mean if we have switched off the main switch, you can now play with the cable that's putting electricity inside, the cable that comes from the box outside there. It does not mean you can cut it because you have switched off the main switch. The cable still provides energy to that box, which says to you and I, there is potential difference here. It does not mean because we have closed or opened the main switch, there is no potential difference on the power source. That box still functions. You can't tamper with the box. You can tamper with everything that the box is connected to, but we cannot touch the box of electricity that's at home because we have switched off the main switch. Now, so that tells you here, the reading that you'll get across the battery here, the reading we get when the main switch is open, we call it EMF. That's the maximum potential difference provided by the battery per unit coulomb of charge. But when the switch is closed, like it is closed here, meaning everything in the house is operating, the potential difference across the battery, this potential difference, this reading here that we find across the battery, this reading is now called the terminal potential difference. It's called the terminal potential difference when the main switch is closed. We get what we call the terminal potential difference. So the reading here on this bulb, here will not be zero because the main switch is closed. TV is operating, lights are operating in the house. The main switch is closed. So everything in the house is working. But if the main switch is opened, everything in the house is not working. Every appliance is not working, but the box where we get electricity, that box still works, still functions. That's why we get EMF. But when the switch is closed, then we get what we call terminal potential difference, which is the one that we see there. So this is a 1 mark question that the examiner would ask you, straight point blank. They will say, switch 1 is still open. Write down the reading on V whatever. It is important for you to remember that when the main switch is opened, the reading across the battery is EMF, and the reading across all external circuit there will be zero. Everything will operate at 0, whereas the reading on the battery will not be 0. Okay, let's move. I'm gonna try and move as fast as I can because I want us to try and solve some few questions as quickly as possible. So this relationship can also be represented in a formula. Now, what does the formula say? Well, the formula says, if I want to get potential difference, the relationship between potential difference and current, if I take the EMF of my circuit, if I take the EMF of the circuit that I have, and I use that EMF, as a function, and I say current here, current will be sorry, technology is technology here. Okay, if I put EMF as a function of current, that means I'm changing current in my circuit. I'm changing current in my circuit. I want to observe how EMF will be influenced when the battery has internal resistance. That means I'm using EMF as a function to current. From the formula that we have been talking about, this is what we can observe from the formula that we have been talking about. That is the terminal potential difference. We are now rearranging it in such that the terminal potential difference becomes the function, our Y, and internal resistance there, and external EMF, our EMF there. EMF subtracting internal. This will be the internal circuit. EMF subtracting internal circuit will give us the potential difference of the circuit, external circuit. Okay. Then if we operate that and put it as a function, what we can see there is that if this is the potential difference is the terminal potential difference, internal resistance becomes the gradient of the graph because current is now our X and EMF becomes the constant. So this graph is important for you to understand. In this graph, you don't normally get EMF. It's actually potential difference versus current. And they will tell you that it has internal resistance. Now, the relationship here that we must know that gradient of that function will be internal resistance. The gradient of the function is internal resistance. Now, the gradient of the function is internal resistance. And at the y, at the y-intercept, where x is equal to 0, when x is equal to 0, when there is no resistance, there is no flow of current in the circuit, we get EMF. When x is equal to 0, that's the y-intercept, we get EMF. So, two things we must take from this. Gradient is internal resistance. Y-intercept is EMF. Now, we must get that. We must get those two things. Please remember them. Those are the two things that we must remember. That gradient is internal resistance. And then, yes, somebody on. Okay. Yes, you can talk to me. You can unmute yourself, Mr. Mundi. Mr. Mundi? Is it an old hand or you are fine? Okay, looks like we have lost Mr. Mundi. We will come back to him. Let us continue in the meantime. Okay, so we need to know two things because the examiner will ask you to calculate the circuit and also would ask you a graph. So when you are looking at the graph will be from this equation. The graph of internal resistance will be from that equation. So you get two graphs in this topic. You get the graph for Ohm's law, and then you also get the graph for internal resistance. Now, so it is imperative that you remember that. If it is with internal resistance, the y-intercept is your EMF, and the gradient of that graph is resistance, internal resistance. If it is Ohm's law, depending on what your x's are, you just go to the formula, look at your x's, and then you have your answer. But with this guy, it is important that we pay attention to what the examiner has assessed us on. Okay. If you look at that graph, you can see now the two graphs that I've projected here. Yeah? Look at the two graphs that I've projected here. We have one graph here, and you can see that it starts there, meaning we can get EMF there for this graph. We have EMF. But remember that the gradient of this graph, if we draw a line of best fit there, the gradient of this graph, the gradient will give us internal resistance. Now, okay, this is the graph that compares resistance. This graph compares resistance for resistor X and resistor Y. Why do we say that? Because they are both straight line graphs, meaning they are both what's the word? They are both ohmic resistors. They are both ohmic resistors, but now we are comparing the resistance. So if you have to calculate gradient of x, if we were to calculate gradient of x, you will see that the gradient of x will be the change in y over the change in x. So what is on my y is potential difference. What is on my x is current. So that means the gradient for this function is actually resistance. We are looking for resistance. The same thing there, we are looking for resistance. So we are comparing resistance of two resistors. And because of that, the one with the greatest gradient will obviously have the highest resistance. And the one that has the lowest gradient will obviously have the lowest resistance. That is the typical type of graphs that you will find in these questions. I want to move as fast as possible because I want us to try and attempt a few things. So there are different types of cases in electric circuits that you and I need to talk about. So I want to highlight those different types of cases. This is just a summary of everything that I've just said. This is just a summary of everything that I've just said. I've been talking about that as well. I've also indicated this, that if the main switch is open, the reading on external circuit will be 0, but the reading across the battery will be there. There will be a reading for the battery. That reading was called EMF. But if the switch is closed, there is a reading on V2, there is a reading on A, and the reading on V1, there will be a reading there, but it will be lower than when the switch was opened. Okay. It's just a summary of what I've just highlighted as well. So let's move on to these are the formulas that we are going to use, but we have highlighted them on that side. You just need to be very careful when you are looking at if you are going to use these formulas. You don't find them on your data sheet. So that means in order for you to use them, you need to have an understanding of what you are looking at. You must have an understanding of what you are looking at. Okay, so this is a flow chart that you can use to answer the questions that will be provided to you. Now, in this flow chart, what we can see is that you have the battery of the EMF. That is the maximum amount of energy provided per unit coulomb of charge. And the first question is, the battery, if it has terminal potential difference, if the circuit is open, we get, if we have an open circuit, and then you also have the other side that says it has internal resistance. Now, so we automatically go there. We just need to find out, does the battery have internal resistance? If it has internal resistance, then what do we do? So that flow chart, you will see I have a summary of it somewhere here that we need to look at. Just briefly, in less than 5 minutes, I'm just going to touch on power. Now, energy. This is the electrical energy provided per coulomb of charge. This is the energy that is provided per coulomb of charge. This is the energy that these charges, as they exit the battery, they are carrying with them. So we use these three formulas to calculate electrical energy. But from this energy, we then need to talk about the effectiveness of a resistor. How is it effective? Now, that is what we call power. When your grandmother sends you to go and buy a bulb at the shop, when you get to the shop, they tell you that you have a 60-watt bulb, you have a 100-watt bulb, and you have a 120-watt bulb. Now, what's the difference between the three? The difference is which one is the brightness. How effective is its function? The purpose of a bulb is to light. But how bright will depend on its power. So if you buy a 60-watt bulb, it will save electricity, but it will be dimmer because the 100-watt bulb will be brighter than it. It will consume electricity, a lot of electricity than the 60-watt, but the 100-watt bulb will be brighter. And the 120-watt bulb will be even brighter, but it will consume a lot of electricity. So you are struck between the three, deciding which one to buy. That is the effectiveness of a bulb. So that is power. Whenever we're talking about power, you need to think about what the resistor is and what does it do. Its power is based on what it does. its ability to perform its duty effectively. So how do we calculate power? We can calculate power in using the 4 formulas that we have here. We can use power to calculate, we can use energy provided over time. We can use potential difference and current. We can use current, resistor, and time provided, or we can use potential difference and resistance. Now, your teacher will tell you which ones do we use to explain, but these two are the ones that we mainly use when we do our explanation. There are those word questions that we need to go through, and in those word questions, these are the 2 formulas that we use to explain what would happen to power if a device was added or a device was removed. These are the 2 formulas that we use mainly to explain power. But remember, power is effectiveness. Now, so from power, you need to be able to calculate energy, electrical energy, the cost of electricity. We need to be able to calculate the cost of electricity. So I want us to start looking at the first relationship here. The first question on grade 12. Remember, I said the examiner will ask you either the graph or the examiner will ask you a circuit. So we need to know both. We need to be able to answer both. Now, if you look at this investigation, it says, let us conduct an investigation to determine the EMF and the internal resistance of a battery. So they are looking for 2 things. They are looking for EMF and internal resistance of a battery. They set up the circuit diagram below as shown, and the potential difference using a voltmeter. They measure potential difference using a voltmeter for different currents. So they are changing current. Now, these learners are changing current and they are observing potential. Why am I saying that? It is important. It is important to know what is being changed and what is being observed. Now, the observed one is dependent, and the one that's being changed is the independent variable. So they are measuring potential difference and they are changing current. Are we fine? Okay. The results of the graph are shown there. The results of this experiment, they are shown there. And they say which one of the measured quantities is a dependent. You see, that's the first question they ask. Which one is dependent? And I said they are changing current. They are observing potential difference. So that means potential difference becomes our dependent because it is the one that we are observing. Which one of the measured quantities is the independent variable? We've already answered that. We said that it would be current. Then write down one variable that must be kept constant during this investigation. One variable that must be kept constant. According to Ohm's law, the first one would be temperature. But that's not the only thing that you're going to keep constant here. Now, you're also going to try and keep external resistance at its minimum. Because you want to observe internal resistance. So you want to try and keep the external resistance at its minimum. It should be the one that you're able to control. So this is what we call a variable resistor. This is the one that you see in a car when you turn the volume up or you turn the volume down. It's the one that you see on your stove, the one when you switch the levels of heat. That's a variable resistor. Now, we are increasing resistance. So that's the one that they are using. So there are a number of things that you must keep constant, but the one that is most common will be temperature. Okay. And then they say use the graph to determine the EMF of the battery. Remember, from what we just said, we said the EMF of the battery. Yeah? We get EMF when there is no flow of current, meaning when the main switch is closed. And when the main switch is open there, we get EMF. So if we open the EMF, that means we have no current flowing to the external circuit, no current flowing out. There is nothing flowing out, then our EMF, we will find it there, where there is no current flowing. That will be 1,5. And then it says calculate the gradient of the graph. To calculate gradient, honestly, we just maths, changing y over changing x. You're looking for points. Already you have 1 point there. That is 0 and 1,5. That's your first point. Now we need a second point. You can find your second point using, this thing. So you can see that is 1 there. We have 1, 0, and then 1,0 meets at that point there. The thick black line here is 0,5. So we just need to find out how many lines do we have inside. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means each line here will be worth something else. So we just divide 10 by, we just divide 0,5 by that, and then you know the value of each line there. And that would give you what you are looking for. So you can use that. It's just analysis of a graph. You calculate the change in y over the change in x. And then it says, which physical quantity is represented by the magnitude of the gradient? Remember, we said the gradient of this graph, is internal resistance. The gradient of the graph becomes internal resistance. So here are one of those with some questions. They say, how does the voltmeter reading change as the ammeter reading increases? Write down, increase, decrease, or remains the same. Use the formula, this formula, to explain your answer. How does the ammeter reading or voltmeter reading change? How does it change as the ammeter reading increases? How is the potential difference changing as the ammeter reading increases? And they're asking us to use this formula. Okay, now I'm going to explain it to you very quickly. We said we have EMF. EMF remains constant. This thing remains constant. Yeah? So EMF is constant. Already what you can see, the relationship here without us even doing any calculation, the relationship here is that they are inversely proportional, because as potential difference increases, does current increase? Yes, current also increase, but they are increasing in opposite direction. Okay. As we increase our current, what we see there is that potential difference is decreasing. Well, it's there. You can see decreased. When you go there, it is there. It's decreasing. When you're there, it is there. So they're inversely proportional. They are decreasing. EMF remains constant. Now, from our formula, we said potential difference is equal to negative IR plus C, which is the constant that we are talking about. This one is constant. So we are observing these two. We're only observing these two. So the question is saying, if we increase ammeter reading, we are talking about current. If I increase current, how does the voltmeter reading, which is the potential difference, how does the potential difference change? We are saying, from what we can observe in that graph, is that as current increases, the potential difference, external, is decreasing. So it decreases. That's the one we are getting out of the way. So the answer to that question is decreasing. Why? Why is that? The reason why it's decreasing is because as we increase current, we are also increasing internal resistance, which therefore means the potential difference, external potential difference, will also decrease because most of the energy is lost into the battery. It's lost to the battery. So what is lost inside the battery makes it difficult for us to gain outside. So as we increase current, we will increase internal resistance. The potential difference lost there will increase. And as a result, external will also decrease. I hope that answer is clear. Okay. Moving right along. I want us to move on to attempting some serious questions now. But this is just typically a question on what we have been dealing with so far. It's just a simple question. It does not have a lot of things that we need to look for. It's just a straightforward, simple question. Okay. So these are the things that we must do when we are solving questions on electric circuits. But I want us to get to the real deal. We only have like 20 minutes left. So I want us to try and do some questions as quickly as possible. Your teacher will give you the slides. I will request that they share the slides with you so that you can look at the approaches that I've written down there. I want us to try some exam type questions a little bit, just a little bit. Okay. This was a Pro Maths paper in 2022. So they are saying the first question there says a pump is connected to water tank to pump rainwater into the house. The pump is rated 750 watts and it is connected to a 250 volt main supply. Okay, now they're asking, what is the current? What current will the pump draw when operating at 240 volts? This question, you're also going to get it. Whenever you are given power, whenever we are given power, most of the time, we are able to get current. Power speaks to current. Now, most of the time, if we have power, whenever they're telling you that the bulb operates at the power off, they are actually telling you the current that's flowing in that bulb. I hope you will remember that. So in this question, they're asking you to calculate current. They have given you potential difference and they're giving you power. So power, by the formula says it's VI. Now, you have potential difference, you have power. So that means they're actually asking you to calculate current. So in every circuit that we're going to look at, once they tell you that the bulb or whatever is operating at the power off, in your mind, you should know that this person is trying to tell you this is the current flowing at that apparatus there. Okay, in the circuit represented below, the battery has an EMF of 12 volts. So we are given the EMF of the battery. An internal resistance of 0.5. That's good. We are given also internal resistance. Okay, the battery is connected as shown to a light bulb and a resistor RX. Both of unknown resistance. Ammeters have zero resistance. Sorry. Ammeter has zero resistance and voltmeter has infinite resistance. So we can ignore the resistance of an ammeter and the voltmeter. Now, they're saying switch S1, there is switch S1. Switch S1 and switch S2 are initially both opened. Before we can answer or look at the questions, we first need to draw the direction and flow of current. What we see is there. So that makes switch S1 a main. That's a main switch. Now, current flowing out is the total current. I total goes to the main switch, and then when it reaches this point, current splits. Some of it goes that direction. That is the current in the RX resistor, and the current flowing in the bulb. That would be, I'll write it 2. That's the current flowing there. And then total current is the one that's passing in A1. So the current passing in A1 is the same current that is passing in S1 as well. Okay, so we now know. We know that the bulb is connected in parallel. It's a parallel connection. Bulb is connected in parallel to the RX resistor. This is the typical example of the table. The circuit that I showed you earlier is a typical example of that. So the first question there was, define the term EMF. EMF is the maximum energy provided by the battery per unit coulomb of charge. What will be the reading on the voltmeter V when both switches are... Hello?
Can you please answer our 8.1.2?
8.1.2, the cost of electricity. Okay. Okay, they said the cost of electricity is 1 rand per kilowatt per hour. Calculate the cost of using the pump continuously for 20 minutes. Okay, I just need a 2-minute break and I want to go to the restroom. Can you just attempt it for a while? Let me just go to the bathroom. I'll be back. 2 minutes. Okay, I'm back. The question was on cost of electricity. I hope you managed to try it. But to calculate cost of electricity, cost, okay. What happened, Manji? Where are we going? Go back. Pen is not right. Just give me a sec.
This one. This one.
It's fine. That one. Let's see. Can you see that color? I hope you can see it. Okay. Cost of electricity is equals to energy used times tariff. Now, tariff is what we have here. That is our tariff. So the tariff is the cost of usage. Now we need to know the energy. Energy, electrical energy, we looked at it earlier on. That's the one that we said that one, capital letter R. So we just need to calculate energy quickly. Okay, let's go through what is given to us so that we can calculate energy provided. So they say the time we are going to use, the time that we are using is 20 minutes. We need to convert this 20 minutes to hours. That's number one. We need to convert that 20 minutes to hours. So that means we have to divide it by 60. And then what else do we have? We're given the power at which the pump operates, and we're also given its potential difference. Now we also still need to find now the current that was pumping it. We need to find that current. Unfortunately, I can't do anything without that current. I can't calculate energy without current. I will ask Daniel to assist me while we are busy calculating the current. Did you manage to get the current there? Talk to me. Did you get the current for 8.1.1? So that is 750. That's 750 divided by 240. So current here, current that it was operating at was 3,125 amperes. Okay, now we need to calculate energy. For it to operate at that, we need to calculate the energy there. So energy that is operating with, we have now potential difference. We have potential difference, we have current. All we need now is energy. So we're going to use the formula that says V I delta T. Remember, we want our energy. That's the energy used. So energy used here will be potential difference, which we said was 240, multiplied by the current that we just calculated as 3,125, multiplied by the time. Our time here, we need to say 20 divided by 60. That's the fraction. It will give us our energy. Or let's just keep it as 20 times 60, but let's continue. It gives us 253,2 watt, but we want it in hours, so we want it in hours. Watt hour. It's 2,3 watt hour. Now we want it in kilo. This is watt per hour here, watt hour. So we just need to convert this. Now we divide it by 1,000 so that it gives us. We divide it with 1,000 so that we get kilowatt hour. So when you divide it then with 1,000, it gives us 0,2532 kilowatt hour. Then you take this energy, you multiply it by 1,2 there. 0,2532 times 1,2, which is the tariff, and that will give you the cost. Cost becomes 0,30, so 30 cents. That will be 30 cents to operate it.
Sorry, sir.
Yes. Talk to me, I'm listening. Talk to me, I'm listening. Just unmute your mic.
Sorry, sir.
Yes, madam.
How did you get the answer? The 253,2.
Which one?
The energy.
Energy.
Yes, sir.
This one.
Yes, sir.
Remember, can you mute a little bit so that the echo does not come back? Okay. We calculated energy. Just
Hello,
hello, sir.
how are you?
I'm good, and yourself, Union.
I'm good. Sorry, sir. How come you convert this duration to second, whereas there we are talking about kilowatts per hour?
Yes.
I don't understand why you decide to use seconds, whereas there we are talking about kilowatt per hour.
Maybe it's me who did not explain the conversion. The time is 20 minutes, né?
Yes,
So we need to convert 20 minutes to hours.
yes.
2 hours, eh?
Oh,
Yes, to hours.
Oh, yeah.
oh, that's right, that's right.
That's why
Oh,
you
yeah.
see, you see
Oh,
that
Oh, I
division by 60.
understand.
And I understand. Thank you.
But we fine.
Yes, sir.
You are also sorted.
Yes, yes.
Okay. So I
Thank you.
wanted to know if I answered the first one first
Oh,
already.
yes.
Does it answer this well? Are we fine? Can I move? Running out of time. Can I move? Okay, can you mute then so that we can, unless if you have a question so that I can answer it. I have to exit so that I give space to the next presenter. Okay, thank you. Okay, dokie. So if you move forward and then you look at the next question that they're asking is what will be the reading on voltmeter V when both switches are open? The voltmeter V when both switches are open. There is our voltmeter V. The main switch is still open, so that means this outside will not be operational. Now, the second outside will not be operational because the main switch is open, so the reading on the voltmeter there will be 0. Okay, that's unfortunately what I have time for today. The slides are available for you to go through with your teacher as well. And I thank you for being here with me today. Goodbye and God bless.
Thank you, sir.
Goodbye.